Yeah, hi everyone. My name is Karthik Poduval. So I'm a principal SDE at Amazon Lab 126. So in my day job, I mostly work with embedded systems, mostly around the cameras, ISPs, and some other video related device drivers for embedded boards on IPs and things like that. So I started using the Yocto project in 2019, and so I think last year for Embedded Linux Conference 2022, I was trying to give a talk about video for Linux memory to memory framework, and I had learned about it in the previous years. So I thought I should, and I found that there was no talk about it. So I thought I'll make a, I'll create some material and then I'll talk about how to write, a driver using V4L to mem framework. And at that point, I was also familiar with Yocto. So I thought I'll also use Yocto to make my job easier. So let's first talk about what were the tenets for the talk, right? So one was it was to just explain the V4L to mem framework, but I also wanted to do it using some sort of example hardware uh, that's virtual in nature as well, so you don't have to go and buy a Raspberry Pi or anything specific, right? The also want to create a reference device driver for that hardware, and finally, some sort of an application and an application image that encompasses all of these components together, right? And wanted to do all of this in an easy to recreate environment. Uh, so I thought Yocto was like the right platform to build all of these things. So the some of the reasons why Yocto is suitable for this demo, one is demo and talk is it is a very suitable. It has a built-in QEMU support, and I would say that I got the idea of implementing the virtual hardware on QEMU because of using Yocto, because Yocto was already doing it. I don't think I would have gone and explored QEMU by myself and done all of these things if Yocto already hadn't had it integrated as its default emulator. So since I'm a device driver developer and this talk is for people who are interested in this, also needed a suitable build system that can build all of these things, right? The emulated hardware, the device driver, some library to talk to it, an application, and finally some sort of a test image, right? And I think Yocto provided all of these. So in addition, I also used a variant of Yocto called the YOE Distro. So that was also very good for this particular project for the following reasons. So YOE maintains a fork of all dependent Yocto layers, and it also makes fixes in them, if there are any problems. Uh, so that basically helps in avoiding any layer patching. If there's some layer troubles, you can avoid that. You also has a built-in Docker. So I think a year later now in 2023, I'm able to reproduce my same build and my environment from last year. And I think as we continue, I'll be able to continue doing so in the years to come because of the Docker that's provided by your distro. And lastly, you also has a couple of different uh, helper commands to do things like adding a layer. You can search recipes, search within recipes, or find recipes themselves. You also has a very simple environment setup scripts, so there's no need to actually do special commands inside local.conf. And then this is the thing I like the most about Yo, that all the conf files are outside of the build directory in a file called site.conf, and that's maintained under Git. So it's easy to now, not have very large number of steps or instructions that go and add this to local.conf. All that is not necessary because site.conf is maintained under Git. So all those settings come in naturally. So with this, how to use Yo to create a layer. So these are some instructions. So you can first check out the Yo distro. Yo does use the Git submodule approach. So that basically allows getting all the different layers into and creating a workspace out of it using the Git submodules. And I like this because of, if you're already used to Git, then Git submodule is a natural extension. And after that is a source environment script, which so for this demo and talk, I was using QEMU ARM virtual machine. So then the source script is called source QEMU ARM environment setup.sh. And this kind of calls all the necessary OA scripts in between and initializes your environment. And also, it doesn't take you into the build directory. That's one more difference, that you always stay inside the root. And but as you build, things get deployed into the build directory. Note that these commands are from last year's version of Yo. The current version has changed slightly a little bit. Um, then the next thing to do is to add the example layer, right, where the actual work is going to be done. So it's called meta v4l2 mem2mem example. And for that, again, your distro has a convenient script. It's called yo add layer, where you can pass the URL and the branch. So basically, this is how I ran it: yo add layer, and I pointed to GitHub uh, uh, URL, and then gave the branch name. So I'd already previously created a boilerplate layer using the bitbake layers create layer script, and uploaded the contents into that kit. So at this point, that empty boilerplate layer came and got added into my Yo distro workspace, and as one of the available layers. So now what exactly goes into this layer? So the first thing, like the first slide, we need um, to modify QEMU to go and add virtual hardware. So this can be done by doing a BB append on the QEMU system native recipe. That's the one that builds QEMU system for AArch64 and that machine, the QEMU ARM64. So that needed to be modified. So here are the changes. So again, I did fork from the QEMU branch, the QEMU project, matching version to whatever I think this was based on Yocto Kirkstone. So based on the matching version, I also cloned the QEMU project to get something very close to that, or it's actually using the same SHA. And then I started adding my virtual hardware changes into that. And so the BB append is only overriding the source URI. Um, and there's some extra things which were needed because I had some QEMU issues, so I had to enable sanitizers. So I did put an extra OEConf append, but it's commented out finally. Um, yeah, then moving on. And then there were some build errors, so I had to remove some package config for libxml and XFS. So yeah, I wasn't planning to upstream this, but yeah, just got through with it by removing those package configs. So now just quickly talking about what the virtual hardware is and how very quickly how QEMU supports addition of virtual hardware. So QEMU basically has a bunch of calls that you can make into virtual hardware. There's things like memory map read, write, which comes from the guest OS, can then actually go on to virtual hardware source code. Virtual hardware can deliver interrupts back to the QEMU machine. And there are also APIs to do DMA transfers. So with all of these APIs, I created a virtual mem-to-mem scaler device. And the actual scaling algorithm was, again, another open source project known as the SDB scaler. So this is basically just tying these things together and creating a virtual hardware. So the created virtual hardware kind of look like this. So that's a data sheet for the virtual hardware. And there's a bunch of registers, some of them being, first one being the input width and height, input stride, output width, output height, output stride. Now, because it's a mem-to-mem hardware, so you give it an input image and an output image, right? And it would either upscale or downscale based on whether the input width and height is smaller than the output width and height, then it would be an upscale. But if the output width and height is smaller than the input width and height, it would be a downscale. So that's kind of how you decide which operation to do. So this very simple hardware only supported one format, which is the BGR format. And then there's also some control and status registers. We could use that to start processing, can enable interrupts. And then there's a status bit 3 and 4 to see if the hardware is idle processing done or done, but has some errors, right? So all of this was implemented in the QEMU backend as a virtual hardware device. So now next thing was to write the device driver. Now the hardware is ready. We need to write a device driver to test the hardware. And also have that driver would also be a demonstration on how to do a V4L2 mem-to-mem driver, right? So this V4L2 mem-to-mem framework is very suitable for this kind of an IP, which is doing scaling. It's some sort of a video processing IP. And it also provides a way to manage multiple contexts for applications. So like, let's say 10 different applications need to use the scaler. So V4L2 framework provides multiple contexts for those 10 applications, and they all would end up sharing the single hardware instance that you have. And there's lots of v4l2 API for doing common things like setting formats, allocate buffers, setting controls, and etc. So all of those things were also available with the v4l2 framework. So very quickly, this is a since it's a Yocto conference, I'll try to keep this very brief. This is sort of a diagrammatic representation of mem-to-mem v4l2 mem-to-mem architecture. So there's multiple contexts. Contexts have buffers, an input and output buffer. And then there's VB2 queues inside the kernel, and then there's mem-to-mem queues, and then finally there is a job queue, which is where the single shared hardware, the hardware gets its actual, the device driver gets all of the jobs from various different client contexts, and once it finishes, it pushes it back, and then the buffers get returned, and this keeps happening again and again. So for the kernel itself, there was a recipe. It's called the V4L2 mem-to-mem scalar driver. And now here's another nice thing that the Linux Yocto recipe provides, and I think other kernel recipes can also do it. The QEMU ARM uses the Linux Yocto recipe, which is a reference kernel that's provided by the Yocto internal layers, OE layers. So in there, there is a very nice feature called SCC. I forget what the full form of it is, but there is a project called Yocto kernel cache, and it has this collection of SCC files, which are a combination of either patches or kernel configs. So for bringing in the video for Linux support into the application image or to the kernel, right, that was getting built, uh, it was very simple. But all we need to do is add this media platform.scc file. So this brings in all the necessary configs to bring in v4l mem-to-mem support. So once this small patch is added to the Linux Yocto BB append, uh, now the kernel gets compiled with v4l2 mem-to-mem support. And this is necessary to compile the out-of-tree driver recipe, which is shown above, the v4l2 mem-to-mem scalar driver.bb. So let's take a look at the recipe for the kernel driver itself. It's pretty straightforward, boilerplate things, and uh, it uses a BB class called module, so which is meant for kernel modules. And the driver itself is on its own GitHub link, so that's the source URI. And pretty much that's it. There's nothing more than that. The other kernel's BB append helps in bringing in all the necessary features to compile this driver. Uh, we need a library to write the application, and there's a lot of libraries available, but I thought of using libcamera because libcamera had really good C++ classes for v4l2 internal functionality, and it was helpful to write a application for this test driver and test hardware. Uh, so for this, again, this was a single append to the libcamera recipe, which is also provided from the internal OE layers. And in here, so the patch needed was to basically export some of the internal headers, because the libcamera public API exports headers that are usable for writing camera-based applications, but for video for Linux memory-to-memory based devices, there are some other helper classes in there that are not exposed to the through the public API. Since patch file was needed to allow for exporting these headers into the public API space, so that an application can link to this library and make use of those helper classes. So that's sort of the only change that was needed here. And finally, an application which is like a C++ based application was written to test everything out. So it used the virtual hardware, the driver that spoke to the hardware, the libcamera based library to use the abstraction methods, and the test application here is called mem-to-mem example.cpp. And what it essentially did is it configured the driver through the libcamera API to and gave it like a input image with some scaling coordinates. And there's a few header files there that's basically it's like an open source image called BBB. So I just used it and created some test vectors offline, and then used the hexdump tool to create a header file of those test vectors. And essentially what was done is inside the input side of the driver, we fed give this image to it, and then let the driver give the job to the hardware. And once the downscaled output image came back, then you could compare it to what is expected. So in some sense, the this is like a test vector which has been created with a C model of the equivalent hardware, which is the STB library, and then we let it run through the entire driver and hardware and compare the outputs to see if they are a match. That means everything is working fine. So it's a test for hardware, the driver, as well as the application. And final thing was to now combine all of these things together and create an application image. So for that, there is an application image recipe, which inherits from core image and adds a bunch of image features. The first line being to just, SSH into the image. And uh, I did run into some issues while debugging this, while writing it and debugging it. So debug tweaks and those features will help in getting GDB and all of the necessary debug tools to debug and diagnose. Uh, and a few other libraries like V4L2 utils, Yocto, and libcamera. Although eventually only libcamera was used, but during the development process, the other tools were also helpful, the V4L2 utils and Yocto. Um, and finally, you include the image, the driver, the the out of tree kernel module driver, and finally the mem to mem scalar test application that brought all of these things together. So if anybody wants to recreate this, it's fairly simple. These are the only steps required. So we need to like git clone the YOE Distro. So I have created a fork for it for this particular talk and demo, and you cd into the directory. You can source the QEMU ARM64 environment setup script. You can build the entire image using v4l2 mem to mem example image, and then launch QEMU. And once we are inside the QEMU, so there is one bug in libcamera recipe, so it doesn't package things properly. I didn't have time to fix it, so that's why this hack had to be done to just fix the symbolic links correctly, and create symbolic links to the actual library. And once that is done, then the application can be run. So I could do a quick demo of this as well. I just have recreated the same environment over here. I will not try to build it. So I've already checked out the source tree, built it, ran the source script and also built everything. So I'm just going to start from running the QEMU. So the QEMU launches over here. We just give it a few seconds. Come on. We need to log in as root. I'll try to copy the contents. So that should create the correct symbolic links that the application is going to look for. And finally run the test. So it's going to basically do what I just mentioned, 5 frames, give it a set of input images, and once the output is received, compare it to the stored test vector. A couple of other things I can just show how the virtual hardware got added here. So we have procs IO mem, and then here we can see the modified QEMU in there actually, and this is the mem to mem scalar virtual hardware that got added. And the actual driver can be seen as seen under like the sys versus platform devices. So that's over here, same at the same index, right? Mem to mem scalar device here. One useful thing that QEMU does is, in addition to creating the virtual hardware, it also creates the device tree for it. that also can be done from within the QEMU. Um, yeah, so I'd just like to say that, Yocto has been very, very, very useful because I thought of doing this. I wrote a proposal, and this whole project took like 2 weeks to implement, mainly because there were a lot of uh, like some bugs that I did in the code which I had to debug. But again, Yocto was very helpful there. Easy edits to recipes, to enable address-based sanitizers, to add GDB, and all of these helped me focus on actually delivering the project. And I didn't have to worry about having a stable infrastructure and a build system that brought all of these things together. So Yocto was a great help, and I don't think this would have been possible without Yocto in such a short time. So I'd really like to thank the all the great contributors to the Yocto project for making this available to everyone. I think that's all I had.